Hey everybody, welcome back to the second lecture on block encodings. So last time we talked about the basic idea of block encodings, how we specify them, and how we can enlarge our Hilbert space in order to be able to take an arbitrary matrix and write it as a subblock of a bigger matrix. And today we're going to be showing how to actually make this concrete, how we can actually implement a specific block encoding for any matrix you feel like. Now, of course, spoiler alert, in general, if you want to build an arbitrary matrix, it's not going to be doable in polynomial time because there's an exponential number in general of matrix elements that we need in an exponentially large matrix. So there's no free lunch that ends up coming in to some extent. But that said, there are a host, of course, of very large matrices that we can block encode. And the tools that I'm going to be talking about, specifically linear combination of unitaries, will give you a method for going forward and building any such matrix you feel like, and in some cases, in polynomial time. So let me begin by sharing my screen, and we will jump in to this. So to begin with, the basic idea of the block encoding was as follows. Let's imagine we've got A, which is in C2 to the n by 2 to the n. Then what we'd like to be able to do is we'd like to be able to build it inside a larger unitary such that the unitary will be of the form A over alpha with some other junk over here. And U will say is U is in C2 to the n plus m times 2 to the n plus m, where these extra m qubits over here are used to specify the particular blocks. Now, in particular, we can often get by with m equals just 1 to be able to do this because, well, we only need one extra qubit in order to be able to specify a particular block that we end up having up here. But that said, if there are many cases where we'll see is actually going to be practical to have many more qubits to encode it. And in particular, this block matrix U is of the form 0, 0. And here, this is the m qubit state tensor A over some normalization constant alpha plus a whole bunch of question marks on all the other blocks. The key point is that all these blocks are orthogonal to it. So those question marks might be of the form um, 0, 1, answer B. Put a question mark down here because we sort of don't care what that is. And then maybe 1, 0, tensor C, question mark, so on and so forth. Key point is that all of these block labels that we have over here, or tags, are all orthogonal to each other, and they refer to these different pieces inside the matrix. Okay, cool. So that is the basic idea of block encoding. And what we do in particular is we introduce the notation where A is then equal to alpha bra 0 tensor identity times U 0 tensor identity. So one thing I wanted to raise, and this has actually caused, in fact, myself even recently, a little bit of confusion, which is what exactly does this mean over here? Now, we're used to tensor products being used in order to be able to define tensor products of Hilbert spaces, tensor products of operators acting on those spaces, as well as vectors. But how do we think about a mixed tensor product between a vector and an operator? The easiest way to think about this is to is to use the fact that operators can be thought of as vectors. I guess I should say, in particular, linear operators can be thought of as vectors in a um, Hilbert space. And in general, we can think about the tensor product of two completely different Hilbert spaces, let's say H1 tensor H2. And in this case, the way we're going to think about this is H1. This is the Hilbert space of the ket 0 in our context. And this over here would be the Hilbert space of the identity when thought of in terms of this. So the question is, what is the notion of a Hilbert space? Specifically, a Hilbert space is a vector space that's equipped with an inner product, an IP between two elements, a B and a norm such that norm of any element in the vector space is equal to the inner product of A with itself square rooted. Okay, so this is the generic definition of what a Hilbert space is. So if we want to claim that operators can be thought of as a Hilbert space, we need to then define what we mean by the inner product on this. And I know that for some of you, this might seem like a little bit of a mathematical digression or some super nerdy topic that probably only Nathan's really interested in. But I assure you, this discussion about the Hilbert space of operators is going to become vital when we jump into LCUs. Just trust me on this. The reason why I'm diving into this will become really clear soon. So the idea now is that we've got this definition of a Hilbert space. So we need to first figure out, well, what's the definition of the inner product? Because the norm can then be thought of as being induced by the inner product. So the inner product, and this is the known as the Hilbert Schmidt inner product. So let A comma B be linear operators acting on a finite dimensional Hilbert space, math call H. Then we define the inner product between A and B is equal to a 1 over the dimension of the Hilbert space times the trace of A dagger B. Now, first off, to note the inner product that we normally think of actually kind of is exactly of this same form. In particular, let's imagine that I had two vectors. I've got psi and phi inside some finite dimensional Hilbert space. If we consider the inner product of psi and phi, this inner product is just given by Dirac notation to be the value of psi phi, which is just equal to the product of psi dagger phi. Okay. And so this is why we end up having this form up here with the daggers in here. It's really just capturing the same structure that we have for ordinary vectors, but allowing us to generalize the result to matrices. Now, in this case over here, we don't need this normalization factor of 1 over dim h to normalize the result. This is just chosen by convention in order to be able to get an orthonormal um, operator basis for matrices. In this case, the output dimension from the product is always going to be 1, so that this factor over here won't be needed in defining the Hilbert Schmidt inner product for just vectors over here. But in this case, if we're to think about them as operators acting on the finite dimensional Hilbert space, and particularly mapping that Hilbert space to itself, we need this extra um, factor in order to be able to make it all work out. So that is the definition of the Hilbert Schmidt inner product. The next thing I'm going to claim is that the Pauli operators on n qubits form a complete orthonormal operator basis on the Hilbert space of 2 to the n dimensional matrices. So what do I mean by that? Well, what I mean, first off, is for the n-dimensional Pauli operators, n-qubit Pauli operators, n-qubit Pauli operators are of the form identity, tensor, blah, 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 tensor, identity, going forward to identity, tensor, tensor, tensor Pauli X. And you can see that they're just constructed by tensoring one Pauli operator with another, going all the way up to z tensor, dot, 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 z. All right. And so the first thing to note is that there are, in general, 4 to the n such operators. Now, if we're taking a look at n-qubit matrices, n-qubit matrices are going to be of the form 2 to the n by 2 to the n, which you should mention, just for the mathematically inclined, matrices are just a representation of linear operators that on a finite dimensional Hilbert space. But I'll often end up using the term matrix and linear operator interchangeably, even though matrices are just a representation of the linear operator. So if we are dealing with Pauli operators over here, the claim is that they form a complete orthonormal operator basis with respect to the Hilbert-Schmidt inner product on the Hilbert space of 2 to the n dimensional matrices. And it's kind of clear, again, from this discussion, that there's no way that we could conceivably have more than 4 to the n such operators, because if you think about it, every single matrix element that we end up having in here is a kind of linearly independent object that we could sum together in order to be able to form the overall matrix. So there's no way that we could possibly have 4 to the n linearly independent, more than 4 to the n linearly independent vectors to represent a 2 to the n by 2 to the n matrix, because, well, there's the trivial orthonormal vector space that we could use in order to be able to define this. Okay, cool. But let's just show that the Pauli operators end up having exactly that property. So first bit is we're going to approach this inductively. So let P and Q be 1 qubit Paulis, i.e., they're in the set identity X, Y, Z. Wonderful. So first thing about Pauli operators that you need to know is that P Q equals negative Q P if Q not equal to P and none are identity. Okay, so Pauli operators anti-commute, in other words. And the next thing, of course, is that P squared equals identity. So if this is true, let's take a look at what the Hilbert-Schmidt inner product is. The Hilbert-Schmidt inner product between P and Q is defined to be 1 over the dimension, which is in this case 2 for a single qubit, trace of P dagger Q. Now, because Pauli operators are unitary and also Hermitian, this is just equal to 1/2 trace of PQ. Wonderful. Now, let's assume that P equals Q. Then what we get is we get that the inner product of P with itself is equal to 1/2 trace identity, which is equal to 1. Okay, next, let's imagine that if P is not equal to Q, then what do we have? Well, we've got a couple of cases. First off is let's consider the case where P is not equal to Q and Q is not equal to identity and P is not equal to identity. Okay, if this is true, then we have 1/2 trace of PQ equals, because of the cyclic property of traces, where you can, for the trace operator, you can exchange the product of matrices inside the trace. This is the same thing as trace of QP, which is equal to minus, due to the anti-commutation property, the trace of PQ. So therefore, we end up having trace PQ is equal to minus trace PQ. Therefore, this implies that the only possibility that we can end up getting is that in this case, the inner product of PQ is equal to 0. Now, let's assume that we're dealing with P not equal Q and Q equals identity. In this case, we end up getting that the inner product P with identity is just equal to 1/2 trace of P. Now, Pauli operators have the property that trace of P not equals 0 if and only if P is the identity. And you can see this just by drawing them out, right? Identity is 1, 1. That has a trace of 2. We have Z. Z's got a trace of 0. X has a trace of 0. And Y has a trace of 0 as well, because a trace is just the sum of the diagonal elements. So we can see then that this implies that the inner product of P and Q equals 0. And similarly, just by symmetry and the fact that P and Q are Hermitian, if P equals identity and Q not equal to P, then this implies also that P and Q equals 0. So we've gone through it, and as a result, we end up seeing that for the two Pauli operators, we have that 1/2 inner product, or sorry, the inner product between P and Q, with respect to the Hilbert Schmidt inner product, is equal to delta Q. Where this is, I'm using a Kronecker delta notation to say that the inner product is 0 if P is not equal to Q and 1 if it's equal to Q. So therefore, all the single qubit Pauli operators form an orthonormal vector space for the single qubit case. But now let's go to the multi-qubit case. So if we go to the multi-qubit case, let P M and QM be M qubit Pauli operators. And further, assume that for M minus 1 qubits, Paulis form an orthonormal operator basis. Okay, so now we have that if this is true, then we can end up saying, well, all right, then there must end up existing two operators, P M minus 1 and P, as well as qm minus 1 and q, such that p is a 1 qubit and is q Pauli, and pm minus 1 and qm minus 1 are m minus 1 qubit Paulis. All right, great. So now let's evaluate what the Hilbert Schmidt inner product is between PM and QM. If we have this, then this is just going to be 1 over the dimension of the Hilbert space, which is 2 to the m here. And I mean the Hilbert space that they're acting on. The next is we've got to worry about the trace here of the PM and QM. Further, I forgot to mention that we're going to assume that P equals PM minus 1 tensor P and Q equals QM minus 1 tensor Q. That was kind of an important fact, but okay, sorry for doing the whole memento style storytelling with this, but in any case, yeah, we're assuming that this is a tensor product with the results, and now we can use this to end up saying that this is 1 over 2 to the m trace, just using a property of tensor products, pm minus 1, qm minus 1, tensor p q. Wonderful. Now, one of the beautiful properties about traces is that they are trace is factorizable across tensor products. So this is pm minus 1, qm minus 1 times the trace of pq. Now, we know that because a pm minus 1 and qm minus 1 are elements of an orthonormal vector space, we have that this is then just going to be equal to delta pm minus 1 by assumption, qm minus 1, and because the times 1/2 trace of PQ, because there's going to be an extra factor of 1/2 from distributing the 1 over 2 to the m minus 1 here to get the inner product. Now, we already argued that single qubit Pauli operators form a complete orthonormal basis for a single element. So we have delta pm minus 1, qm minus 1 times delta pq. Now, in this case, we've got, we're ensuring from this that this is 1 if and only if pm minus 1 equals qm minus 1 and p equals q. This implies that this must hold if pm equals qm. And therefore, this is just delta pm qm. And thus, this demonstrates the inductive step of our argument. So therefore, for all n Pauli operators, form a complete orthonormal basis. Okay, wonderful. And as a corollary of this, we can use Pauli operators to be able to express any operator. So in particular, what I'm going to do is I'm going to take a look at our friendly matrix A that we're interested in. So let A be a operator that can be represented as a matrix on n qubits. Then what my claim is that there exists a set of different values. Let's call this alpha 1 through to alpha 4 to the n, which is a subset of the complex numbers. and let P set Pi from I equals 1 to 4 to the n be the n qubit Pauli operators. Then in this case, we end up having that A then can just be written as the sum over I of the, yeah, sorry. What I should say is that A is equal to sum over I, alpha I, pi for alpha I equals the inner product of pi and A. Okay. And so the way that we can end up seeing this is as follows. Let's assume that we have a expansion like this. So if A is equal to the sum over alpha I pi's, then what we have is we can just end up computing what the inner product is of vector A on the left with any other vector we feel like. So let's do this for the Pauli operators, which again form a complete orthonormal basis. So if I end up taking the inner product of Qi with A, then what I'll end up getting is I'll end up getting that this is going to be, or let's call it Qj over here, that this will be the sum over I, alpha I, just by linearity of the inner product of Qj and Pi. Okay. Now, if this is true, then what we have is from the definition of the inner product, because Qj is a Pauli operator and Pi is a Pauli operator, then this is just the sum over I, alpha I, delta ij, which is just equal to alpha j. So therefore, what we have to have in order for any such expansion to end up holding is we have to have that these expansion coefficients alpha I are just equal to the inner product of A with respect to the Pauli operator. And in particular, a useful expression for this is just sum over I 1 over 2 to the n trace of Q, let's call it actually PJ over here, or no, PI, A, PI. Okay, so why are we interested in this? Well, getting back to what our original topic was, this ends up showing that all 2 to the n by 2 to the n complex value matrices can be written as a sum of unitary matrices. And in particular, these unitary matrices can be picked to be polys. So this shows that all matrices can be written as a sum of unitaries. So this means that if we were able to come up with a method to end up doing the following, if I say, okay, let's let A be the sum over I, alpha I, UI, where these UIs could be Pauli operators, but they could be something else. If I could come up with a method that allows me to build inside a larger unitary U, the sum over I, alpha I, UI divided by alpha, inside a block of that larger matrix, then by picking the UIs to be Pauli operators, I could actually build anything I wanted inside this. So that's why we made this digression to talk about the Pauli operators as a basis for all 2 to the n dimensional matrices. Is that once we have that, we can see any A that we would like to block encode, we can always write as a sum of matrices. Thus, we can reduce the problem of block encoding a general A to the problem of figuring out how to add up a bunch of matrices on a quantum computer. And that takes us to our next topic, which is the method that actually does all of this, which is linear combinations of unitaries, or LCU. Okay. So, yeah, as I've remarked in my videos, but I'm amused by the story, is that for me, this question kind of popped up in my head when I was a late graduate student. I was going through trying to figure out, just trying to find some time to kill towards the end of my PhD, thinking about stupid things. And one of the stupid things that occurred to me was I thought it was weird that I knew how to multiply matrices on quantum computers, but I had no idea how to add them. And so this foray into LCU started out because of this discussion and really kind of only got fully formalized during my postdoc with Andrew Childs, where we figured out how to uh, do the present formalism that you see right now. So in any case, the moral of the story is I do strongly encourage all of you watching this to occasionally spend some time trying stupid things because occasionally they work out really nicely. But in any case, let's take a look at the formalism of linear combination of unitaries. Um, Assume you have A, which is written as sum over I, alpha I, u I, for alpha I greater than or equal to 0. Now, this assumption that alpha I greater than or equal to 0, it actually technically isn't needed. You can do a slightly more complicated way of dealing with the initialization for the algorithm I'm going to be telling you about that won't end up requiring this. But just for simplicity, let's take this assumption to be true without loss of generality. The reason why is that if we didn't have that, if I ended up having A in general is equal to sum over I, absolute value of alpha I, e to the I, phi I, ui, then what we can do is we can just say, well, let's rebracket this whole thing. This can now be written as a sum over absolute value of alpha I, e to the I, phi I, ui over here. Now these are just a new set of unitary matrices. So we can, if this assumption wasn't true, and we wanted to have negative or complex weights to the individual unitaries, we can always absorb that complex weight into the unitary in order to be able to make that assumption true. So without loss of generality, we can always assume that the AIs are greater than or equal to 0, which again, not needed technically, but it'll make our discussion a lot easier. So let's stick with that assumption. Great. So now we have such a decomposition. In order for us to be able to load into an algorithm that will be able to block encode A, we have to be able to provide information to the quantum computer about what the values of alpha you want are and what the particular u's you want are. And we do this by assuming a kind of common interface to be able to provide these alphas. And this interface we refer to as the prepare and select oracles or circuits. Technically, circuits would be an implementation of these black box oracles that we're thinking about, but call them either way you want it. People will understand what you're saying. The definition of prepare, which is often just abbreviated to prep, is that it is an operator acting on a m-dimensional Hilbert space. So it maps C 2 to the n to C 2 to the m. And a prep has a following action. It's defined to be that prep acting on 0 is equal to the sum over I square root of alpha sub I divided by normalization constant square root alpha. Now, it's no coincidence I called it square root alpha. This, if you recall, with the block encoding, our target was to build an A over alpha over here, right? This alpha that we see actually is going to correspond directly to this alpha that we see over there. So in any case, that's true. And just for clarity, alpha in this case is just equal to sum over I, alpha I. All right, great. So that is the definition of prep. Select is is the second. It gives us a second piece of information. Prep gave us the information about the alpha i's. But in order to build the sum of unitaries, we need to also know the unitaries that we're adding together. So those unitaries are, of course, the UIs. And this will end up mapping now the space of the this over here, which unfortunately I said it was n-dimensional. Let's make it m-dimensional by the power of sloppiness. So if this is m dimensions over here, this is now m qubits. Then select will end up mapping a vector space that's dimension 2 to the m plus n to 2 to the m plus n, and it is a unitary that has the following form. It is equal to sum over I, tensor ui. Okay, wonderful. And my claim is now, this is probably the most important lemma of this discussion. It's called the LCU lemma. And the claim in the LCU lemma is that zero tensor identity prep dagger select prep zero tensor identity is equal to A over alpha, where A is defined to be sum over I, alpha I ui. All right, great. So now one of the things that's nice is that contrary to previous, um, the original definitions that Andrew and I had in here, this derivation is actually a little bit easier to do now that we have this notion of kind of the block projectors on the left and right. So what we're going to do with this is we're just going to act with prep here and prep dagger there. So this then is equal to the sum over ij square root alpha I, alpha j divided by alpha of I tensor identity from the prep acting left. Now select we won't quite have done yet. And now this will be J tensor identity. Okay, so I've just done the prep right and left using the definition. Note that here prep is only defined to act on 0. We do not assume that we know what prep's action is on any other input, because the truth is we don't need to. That information would be useful if we cared about what was actually being encoded in the rest of the blocks. But for this lemma, we only care about what's showing up at the top. So that's why we only need to have prep defined on 0. And it could have, we could choose its action to be anything we feel like on the rest of the space to minimize the cost of doing the block encoding. Anyways, so this is the representation that we've got. And so now let's just expand the definition of the select circuit. So this will be alpha I, alpha j divided by alpha I tensor identity sum over k tensor uk j tensor I. Okay, now we can see then from from orthogonality that those two indices will be 0 unless they're both equal to k. So therefore, this can be written as sum over k square root of alpha k squared divided by alpha k tensor identity times k tensor uk, which is just equal to sum over k alpha k uk divided by alpha, which is just by definition a over alpha as claimed. So this shows that we can how we can use LCU in order to be able to block encode literally any operator that we feel like. So that's pretty neat. Now we'll go into greater detail about the kind of amazing things that we can do with the LCU lemma, but let me just begin with a simple example that will end up giving you a hint of the neat stuff that we can do with it. So let's go through an example of this where I'm going to go and actually build the circuit for implementing a particular LCU. So let's say we want to do, um, let's let A equal e to the I, AX plus BY plus CZ for A, B, C in the real. Okay, so how can we go about building this operator? Now, obviously, this is an example of a single qubit Pauli operator. We could actually just figure out an Euler angle decomposition to boil this down into three RZ rotations. So synthesizing this using conventional methods is straightforward. But let's go about building it as a block encoding inside using LCU. So in this case, first, this isn't actually quite of LCU form. This is written as an exponential of unitaries, not a sum of unitaries. So now let me, of course, give you the second biggest thing that I found has changed my life, which is if the going gets tough and the tough can't solve their problems by going to a higher dimensional Hilbert space, tough will solve their problems by using Taylor's theorem. So in this case, what we have that we can write J or A in the following way. We'll sum this from J equals 0 to infinity of I AX plus BY plus CZ to the J divided by J factorial. Now, one of the things that's actually really beautiful about Pauli operators, as I alluded to before, is that they anti-commute. And while anti-commutation doesn't make life quite as simple as commutation, it's almost as good. And for the purposes of LCU, it actually ends up being about as powerful as commutation is for product formulas. So see why. Let's take a look at what we end up getting. Well, if I explicitly expand this out, zeroth order term is just identity in this. Then we have AX plus BY plus CZ as a linear term. And then, of course, we've got negative 1/2 of AX plus BY plus CZ all squared and dot, dot, dot. Now let's take a look at this guy over here. Well, if I expand this out, I'm going to get AX plus BY plus CZ is equal to A squared plus B squared plus C squared identity plus A B X Y plus Y X plus A C X Z plus Z X plus see, we've done AB, AC, and I guess we got BC is the only other combination left. YZ plus ZY. Now, you'll note that because of anti-commutation, we have that XY equals minus YX, and so on and so forth. So these guys cancel, these guys cancel, and these guys cancel, meaning that actually all that we have left is the identity term. So now, just for notational simplicity, because this guy is going to show up over and over and over again, I'm going to define omega squared to be equal to a squared plus b squared plus c squared. Okay. So then using this language, we can end up seeing what'll happen. If I end up getting ax plus by plus cz cubed, this is just going to end up giving me omega squared times ax plus by plus cz. Cool. So then basically what ends up happening is we end up getting this alternation in the Taylor series expansion where every even term, it's going to be proportional to identity, and every odd term, it's going to be proportional to this. Putting this all forward, what we end up getting is we end up getting that from this sum over j I ax plus by plus cz to the j over j factorial is just going to give us the following. It will end up giving us um, cosine omega identity plus I sine omega ax plus by plus cz over omega. Just by using this pattern and substituting it in here, you can see immediately that this ends up forming from this over here cosine of omega t, because this term um, over here is yeah, it ends up exactly matching that pattern, because for the squares, this is just omega squared. So we clearly see that the even terms will give us this. The odd terms will have this extra power of ax plus by plus cz, but are lacking the corresponding power of omega squared. So we have to divide by omega in order to be able to make that work out. So that's why there's this extra factor of omega on the bottom in order to be able to get the Taylor series to match. All right, wonderful. And now this is a linear combination of unitaries. So if I was to build now a prep circuit for doing this, I can see that, well, first off, let's define alpha 1 is just going to be cosine omega identity, and then alpha um, 2, well, actually, sorry, there's no identity here. Alpha 2 will be equal to sine omega A over omega. Alpha 3 equals sine omega B over omega. And alpha 4 will be equal to sine omega C over omega. All right, wonderful. So now what we need to do is we need to then build our prep circuit. So prep, what will it do? Prep will map now 0, which I'm explicitly going to write as a 2-qubit state. Now, it will map us over to square root of cosine omega, say 0, 0, plus square root of sine omega A over omega 0, 1, plus so on and so forth. Okay, now select will be equal to the operator 0, 0, tensor 0, 0, tensor identity, because for this input over here, we want to have the identity coefficient. And then what we're going to do is we're going to say, okay, 0, 1, 0, 1. We like this to correspond to the x component. So we will have I x for that, plus 1, 0, 1, 0, tensor I y, plus 1, 1, 1, 1, tensor I z. Okay, cool. So now this is one way that we could do it, but the problem is just a question of how are we going to carry out all of the i's that we get multiplied by each of these individual terms. The easiest way to do this is to note that the operator that we're carrying out is only defined up to a global phase. So if we only care about it to a global phase, what we can do is we can say, well, let's put a minus I phase here. If I put a minus I phase on the 0 input and remove everything else, then I can end up forming the exact same thing by deleting all of those phases because these are exactly the same up to a global phase of I. Now, all I have to do is build a circuit that will return a phase of minus I if the input is 0, 0. So in particular, this circuit can be constructed in the following way. What we can do is we can say, all right, well, let's build a input circuit that has X, then a 0 controlled S dagger operation, and then X. And this will return, have the action that 0, 0 will go to minus I, 0, 0. Okay. And everything else will just get mapped to itself. Okay. So that is handles the first term. Now let's deal with the rest of them. So if this is the state that we want to transform down at the bottom, the second register, all that we need to do is fill in the rest of the control patterns that we end up seeing for it. So let's let this one over here be the most significant bit. So then if this is the most significant bit for our encoding, we could do it like this, X, control Y, and controlled Z. Okay. And this will end up giving us an implementation for our select circuit. So then the overall circuit will end up looking like U for our block encoding will be of the form grep here, X, a stagger controlled, and then another X here. And this is our target state down here that we're going to do. And this will be X, Y, and Z. And then we will have prep dagger up here. And in practice, if we wanted to implement this, what we could do is we could say, okay, well, let's prepare 0 in here. And then we measure these over here. And in the event that we get 0, 0 for our two measurements, then we'll have built the block encoding of the unitary that we wanted to construct. So this is an example of how we can go forward and build a unitary of this. Now, it's worth noting that in this particular case, the success probability that you end up getting will not necessarily be 100%. And this can be dealt with in a number of different ways. There's ways that we can perform based on the measurements, controlled Pauli operations in order to be able to flip signs of some of the individual operators that may not have turned out correctly. So there are ways that we can end up addressing this. Also, in this case, because the target is unitary, there are other results that we'll be covering later, such as oblivious amplitude amplification, which will allow us to boost the success probability up to 100%. But the main point of this example was to give you some hints about how we could think about doing Hamiltonian simulation. In this case, over here, that we were doing as an example, is one of the simplest Hamiltonians that you could think of. It's a Pauli X, a Pauli Y, and a Pauli Z term on just a single qubit. And we came up with a method that allows us to generically simulate that. So what I'm going to be covering in the next lecture is to take a look at an application of these ideas to Hamiltonian simulation and show how this idea I alluded to, called oblivious amplitude amplification, can be used to boost the success probability from something that is usually going to be order 1 to essentially 100%. All right, thank you very much, and hope to see you all next time.